Okay, this is number 6 in section 9.5, and as in number 5, we want to use the limit comparison test to determine the convergence or divergence of the series. So again, we look at this series here, 2 to the n over 3 to the n plus 1. As n approaches infinity, this behaves like 2 to the n over 3 to the n. And that's a geometric series, and the ratio, if I write it as 2 to the n over 2 to the 3 over n, or 2/3 to the n, the ratio is 2/3, and that's less than 1, so this converges. So this comparison series that I'm going to use converges, so we'll check the limit comparison test to see if this also converges, if they behave the same way. So we can take this series over this series. This is the limit comparison test. We take the ratio there, or it's not the ratio, but we'll take the limit as we take this kind of ratio test. I don't want you to confuse that with the ratio test, but we take that pure ratio there, and we can just write this as 2 to the n over 3 to the n plus 1, and we can invert and multiply, and we have 3 to the n over 2 to the n, and the 2 to the n's cancel, so we're looking at this limit. Okay. And if we look at this, they basically behave exactly the same because of that. I mean, that's kind of why we picked it. So it's kind of obvious, and I'll show you an easier way we could do this, but it's obvious that this limit is 1, because as infinity gets really, as this n gets bigger and bigger and bigger, again, this one is insignificant, so I could think of that ratio as the limit, which is just 1. So since 1 is between 0 and infinity, and this converges because it's a geometric series with r is less than 1, then this converges by the limit comparison test. And just take a note of this, that since 2 to the n over 3 to the n plus 1 is less than 2 to the n over 3 to the n, remember, if I take this fraction, if I make this denominator bigger, it creates a smaller fraction. So this fraction would be smaller than this fraction, because this denominator is bigger than that denominator. That means that these terms are always smaller than these terms, so we have convergence. In other words, because this converges, this would converge by the direct comparison test. So actually that would have been an easier way to go. But since the directions were to use the LTC, that's what we did. But like I said, if you were going to do that, the direct comparison test would be real easy to do. Okay, and then number 7, we just want to determine whether the series converges or diverges. There may be more than one correct way to determine the convergence or divergence of the series. So try to do these a variety of ways just so we can get to practice. And the one I don't use a lot is the integral test, so I like to practice that. So I use that whenever I get a chance. This is too crazy. So this is the summation, n equals 1 to infinity of 5 over n plus 1, so this could be my f of x, 5 over x plus 1. For x greater than 1, this is CPD, continuous, positive, and decreasing. So I know that this series will behave like this improper integral, and I'll let b equal infinity, so I'll evaluate it from 1 to b, 5 over x plus 1 dx. And this is just 1 over u du, it's a natural log, and I'll have a factor 5 I can bring out, so it's the natural log of x plus 1. From 1 to infinity, and that's going to be the limit. And I can bring, like I say, bring the 5 out even in front of the limit if I want, but I can bring the 5 out in front of this evaluation because it will be multiplied out by the distributive property. And this would be the natural log of b plus 1 minus the natural log of 1 plus 1. That's just the natural log of 2, but that's really not relevant. The relative part is that this is going to go to infinity. As b gets bigger and bigger, remember the natural log is an increasing function, it's just going to get bigger and bigger. So since this goes to infinity, this limit goes to infinity, therefore this integral, this improper integral does not have a value, so it doesn't converge, it diverges. So since it diverges, we can say that this series that we're comparing with diverges by the integral test. We're not comparing it with, but linking it up with this series which goes with this integral, diverges by the integral test. Okay, that's number 7. And let's take a look at one more, I think, number 8. And this is a nice easy one. It's kind of what we call a stocking stuffer, real easy problem. Okay, the summation from n equals 1 to infinity of 3 over the square root of n, that's the summation from 1 to infinity of 3 over, and that's the same thing as n to the 1/2 power. I can put that 3 in front, and so this is what I have. And this diverges by the p-series test because the exponent there is less than 1. It's got to be greater than 1 for it to diverge. Less than 1, it doesn't diverge. So that's easy. So it diverges by the p-series test since p is less than 1. Okay, hope those help.